good evening. Settle in, close your eyes, and prepare for a journey to the very edge of our understanding of reality. Tonight, we won't be discussing stars as mere gas giants or galaxies as simple clumps of matter. Instead, we'll ponder a question that sounds like science fiction but is increasingly debated by serious scientists and philosophers. What if everything we see, everything we feel, the entire vastness of the universe isn't real? What if you and I are living inside an unbelievably complex computer simulation? This thought might seem unsettling, but let's approach it as a fascinating intellectual puzzle. In this lecture for sleep, we will calmly and methodically unpack the arguments suggesting that our world might be artificial. We'll dive into the realms of quantum physics, cosmology, and philosophy, looking for hints and clues woven into the very fabric of existence. Prepare to question everything you thought you knew about reality. Before we delve into the modern scientific debates, it's crucial to understand that the idea that our world might not be real is as old as philosophy itself. As far back as the 4th century BC, the great Greek thinker Plato proposed his famous allegory of the cave. He imagined people chained inside a cave, only able to see shadows cast on the wall by objects passing behind them. For these prisoners, the shadows were the only reality. They were unaware of the true world, the world of forms that generated these reflections. This metaphor was Plato's attempt to explain that our sensory experience might be nothing more than a faint reflection of a truer, higher reality. Centuries later, in the 17th century, the French philosopher René Descartes took this concept even further. In his Meditations on First Philosophy, he introduced the thought experiment of the evil demon, an all-powerful deceiver capable of creating a complete illusion of the external world, including our own bodies within our minds. Descartes asked, how can we be certain that everything around us isn't the result of such a grand deception? For centuries, these ideas remained strictly within the realm of pure philosophy. But everything changed with the arrival of the digital age. The rise of computers, followed by the creation of increasingly realistic video games and virtual reality systems, moved this concept from metaphysics into the technologically possible. We ourselves have learned to build artificial worlds. And this forced us to ask the next logical question. If we can create simulations, is it not possible that we are currently living inside one ourselves? Let's begin with the very foundation of the modern simulation hypothesis, the landmark paper that sent shockwaves through the academic world in 2003. We're referring to the simulation argument, penned by Nick Bostrom, a Swedish philosopher then working out of Oxford University. Bostrom didn't claim definitively that we are living in the Matrix. Instead, he proposed an elegant logical framework known as the trilemma. He stated that at least one of the following 3 propositions is almost certainly true. Proposition 1. Civilizations like ours almost always become extinct before reaching the so-called post-human stage. This is the point at which a civilization possesses technology so advanced that it can create reality simulations indistinguishable from the actual world. Perhaps there are certain great filters that no civilization can overcome: nuclear war, catastrophic pandemics, asteroid strikes, or resource depletion. If this is true, then simulations simply won't ever be created. Proposition 2. Any post-human civilization is extremely unlikely to want to run simulations of their ancestors or worlds resembling their own. Perhaps they will have radically different interests, or maybe running such ancestor simulations will be deemed unethical or simply boring. If this holds true, then even with the requisite technology, simulations will not be created. And finally, Proposition 3. We are almost certainly living inside a computer simulation. Bostrom's logic here is straightforward. If the first 2 propositions are false, it implies that civilizations routinely reach the post-human stage, and they actively create vast numbers of simulations. If this is the case, the sheer quantity of simulated realities would be immeasurably greater than the one single base reality. Consequently, if you consider a random observer, such as you or I, the probability of existing within one of those billions of simulations would be vastly higher than the chance of existing in the unique, original, underlying reality. Thus, Bostrom presents us with a stark choice. Either humanity is doomed, or our descendants will have no interest in creating virtual worlds, or we are already inhabiting one of those worlds. And that choice is truly profound. Let's take a closer look at the probability core of Nick Bostrom's argument, because that's where its truly provocative power lies. Imagine a massive probability tree. At its root is the base reality, that original, true world. Suppose a civilization in this world reaches a technological level capable of creating simulations. They decide to run, say, 1,000 simulations of their past to study it. In each of those 1,000 simulations, a civilization might also evolve, reach technological maturity, and launch another 1,000 simulations of their own. This process can repeat endlessly, creating a cascade, a stack of nested realities. Now let's count the number of existing minds. In the base reality, let's assume there are 10 billion people. On the first level of simulations, we already have 1,000 worlds, each with 10 billion simulated beings, giving us 10 trillion minds. By the second level, the number of simulated minds reaches 10 quadrillion, and so on. As you can see, the number of simulated observers grows exponentially, while the count of real observers in the base reality remains fixed. Now, if you are a random consciousness selected from this entire massive set of existing minds, what is the probability that you ended up in that one solitary base reality rather than in one of the quadrillions of simulations? Statistically, the odds are vanishingly small. It's like a lottery. Imagine there is one white ball and a billion black balls. You draw one at random. What are the chances it's white? Almost zero. In this analogy, the white ball represents the base reality and the black ones are the simulation worlds. It is this simple yet powerful statistical argument that leads figures like entrepreneur Elon Musk to claim that the probability we live in base reality is 1 in billions. Musk argues that we should actually hope we are in a simulation, because if we are not, then according to Bostrom's trilemma, it most likely means humanity simply won't survive long enough to ever create its own simulations. Let's shift gears now, moving past philosophy and statistics and diving into the strangest, most enigmatic corner of modern physics, quantum mechanics. This is precisely where some researchers find the most compelling hints that our reality might not be what it seems. One of the most famous and deeply counterintuitive phenomena is the so-called observer effect. The simplified core concept is this: elementary particles, such as electrons or photons, behave differently depending on whether or not we are observing them. When a particle is not being watched, it acts like a probability wave, meaning it can exist in multiple places simultaneously. This state is known as superposition, but the moment we attempt to measure its location, its wave function collapses, and the particle instantly materializes at one specific point. The most famous demonstration is the double-slit experiment. If you fire a stream of electrons through a screen with two slits without observing them, they create an interference pattern on the backstop, just like ripples in water. But introduce a detector near the slits to figure out which slit each electron passed through, and the interference pattern immediately vanishes. The electrons start behaving like ordinary particles, leaving only two distinct bands. This suggests that at a fundamental level, reality itself exists in an undetermined probabilistic state until the act of observation pins it down. Proponents of the simulation hypothesis see in this a striking analogy to how video games and virtual reality operate. Consider a massive, complex video game. The computer doesn't calculate and render the entire game world in full detail at every moment. That would demand colossal computational resources. Instead, it only renders, meaning it creates in detail, the portion of the world that is currently in the player's field of view. Everything behind the character or over the horizon exists only as simplified data or probabilities. But the instant the player turns the camera, the system instantly calculates and renders the new view. Could the observer effect in quantum mechanics be something similar? Perhaps the universe's processor is conserving resources and reality is only rendered in high resolution when a conscious observer focuses attention on it. As we continue our deep dive into the nature of physical reality, we encounter yet another intriguing concept that aligns beautifully with the simulation hypothesis. This is the idea of discreteness, or to put it more simply, the pixelation of our universe. We are accustomed to perceiving space and time as continuous smooth, like an infinitely divisible line. We can mentally zoom in on any segment of space over and over, feeling like we will never reach a limit. However, modern physics, specifically string theory and loop quantum gravity, suggests this might not be the case. There is a hypothetical minimum unit of length, a size below which nothing can exist in our universe. It's called the Planck length, and it measures approximately 1.6 times 10 to the power of minus 35 meters. This is an unimaginably small value. To truly visualize this, imagine an atom. Now enlarge that atom until it is the size of the entire observable universe. At that scale, the Planck length would be roughly the size of a typical tree. Similarly, there is also Planck time, the minimum quantum of time required for light to travel the Planck distance. It is the shortest conceivable span of time. If these theories are correct, it implies that our reality, at its most fundamental level, is not analog and continuous. It is digital and discrete. It is composed of tiny, indivisible pixels of space and ticks of time. And this structure bears a striking resemblance to digital information. Any image on your computer screen, no matter how seamless it appears, is actually built from a finite number of pixels. Any digital audio is made up of separate samples. Any computer simulation, no matter how complex, fundamentally operates using discrete units of information, bits. If our universe is fundamentally discrete, this becomes a powerful argument that the universe itself is the result of computation. Simulating a truly continuous analog reality is infinitely difficult. It would demand infinite computational resources. However, simulating a discrete, pixelated reality is perfectly achievable, even if it requires an extremely powerful computer. Therefore, the existence of a fundamental resolution limit in our reality might not just be a property of physics, but rather a technical limitation, a hardware constraint imposed by the system running our simulation. Now let's turn our attention to the forces that govern our universe. We're talking about the fundamental laws of physics, gravity, electromagnetism, and the strong and weak nuclear forces. These laws are described by surprisingly elegant and precise mathematical equations. But perhaps the most astonishing thing about them is their sheer universality and immutability. The law of universal gravitation applies equally whether we're talking about an apple falling on Newton's head or distant galaxies orbiting each other billions of light years away. The speed of light in a vacuum is a fundamental constant, the same for every observer, regardless of their location in space or time. These laws seem utterly unshakable, woven into the very fabric of reality. They have held true since the first moments after the Big Bang and will continue to hold until the very end. For proponents of the simulation hypothesis, however, this highly regulated system looks extremely suspicious. Why should reality conform to such a strict, unwavering set of rules? Doesn't this sound exactly like the operating mechanism of a computer program? Any complex piece of software, be it an operating system or a detailed video game, relies on a core set of rules and algorithms, its underlying code. This code determines how objects in the virtual world interact, essentially defining that world's physical laws. Game characters cannot pass through walls, not because the walls are real, but because the code includes an algorithm for collision detection. Gravity in a game pulls objects down, not due to an actual gravitational field, but because a programmer set a force vector to act on every object. In this analogy, fundamental physical constants, such as the gravitational constant, the speed of light, or Planck's constant, look suspiciously like variables defined at the very beginning of the program's execution. Someone, let's call them the programmer, entered these values, pressed run, and our universe began developing in strict accordance with the rules embedded within it. This concept also offers a new perspective on the so-called problem of the universe's fine-tuning, which we will explore further later. If the laws of physics are merely software code, then it suddenly makes perfect sense why they are so ideally tuned for the emergence of life. They were simply written that way. Our universe has an absolute speed limit. Nothing that possesses mass can move faster than the speed of light in a vacuum, which is roughly 300,000 kilometers per second. This isn't merely a technical barrier that we haven't figured out how to bypass yet. It's a fundamental law of nature, deeply embedded within Einstein's theory of relativity. As an object approaches the speed of light, its mass begins to increase, time slows down for it, and achieving that velocity would ultimately require an infinite amount of energy. But why does this limit exist at all? Why isn't it 400,000 kilometers per second? Or why isn't speed simply infinite? Within the context of our natural physical reality, there is no simple, intuitive answer to this question. It's simply a characteristic of our world that we must accept as a given. However, when viewed through the lens of the simulation hypothesis, the existence of such a restriction suddenly seems highly logical. Any computer simulation runs on some form of hardware, a processor, and every processor has a performance ceiling, a maximum clock speed. It can only execute a finite number of operations per second. The speed of light in our supposed simulation could be the exact equivalent of this maximum data processing rate. It might represent the absolute limit at which the universe's processor can relay information about cause and effect from one pixel of space to the next. Imagine our universe as a colossal three-dimensional grid. Any event in one cell of the grid can only affect neighboring cells in the next system tick or clock cycle. The maximum speed at which this influence can spread across the grid would be precisely what we perceive as the speed of light. This analogy also helps explain certain paradoxes of relativity, such as time dilation. In computer systems, when the processor is overburdened with complex calculations in one area, the overall system performance often drops. Perhaps when an object is moving at near light speed, the processor dedicates so many resources to its calculation and rendering that the object's refresh rate, which we perceive as the flow of time, is drastically reduced. Thus, the universal speed limit, which seems so arbitrary and peculiar in the physical world, becomes a perfectly natural restriction of computational power in the digital one. Let's now turn our attention to one of the greatest enigmas in modern astronomy and cosmology, the Fermi Paradox. Back in the mid-20th century, the brilliant physicist Enrico Fermi was having lunch with his colleagues when he posed a simple yet utterly baffling question. Where is everybody? The core of the question is this. Our Milky Way galaxy contains hundreds of billions of stars, many of which are similar to our own Sun. We now know that many of these stars host planets, some located in the so-called habitable zone where liquid water can exist. Given the universe's age, nearly 14 billion years, alien civilizations have had more than enough time to evolve, achieve interstellar travel, and colonize the entire galaxy. Even traveling at very slow speeds, the whole galaxy could be settled in just a few tens of millions of years, a mere blink of an eye on a cosmic timescale. Yet we see absolutely no convincing trace of their presence, no radio signals, no gargantuan megastructures, and certainly no spacecraft. Space appears empty, silent, and sterile. That is the Fermi Paradox, vast numbers of potentially habitable worlds on one hand versus a profound absence of contact on the other. There are many hypotheses attempting to solve this mystery. Perhaps life is incredibly rare, perhaps intelligent civilizations inevitably destroy themselves, or maybe they are deliberately hiding from us. But the simulation hypothesis offers its own, very elegant and slightly chilling solution. What if we are alone in the universe simply because no one else was ever planned? If our reality is a simulation created specifically to study the emergence and development of human civilization, the programmers would have no reason to create other sentient species. It would be an unnecessary complication and a waste of precious computing power. In this scenario, the distant stars and galaxies we observe through telescopes might be nothing more than background assets, beautiful, non-interactive scenery. It's like a video game where you can see painted mountains on the horizon, but you can never actually reach them. The universe might be vast, but it is only truly habitable and rendered in detail in our immediate vicinity. Thus, the Fermi Paradox ceases to be a paradox. We don't see aliens for the same reason that background characters in your favorite novel never suddenly start living out their own complete lives. A powerful, indirect argument supporting the idea that our reality might be artificial comes from the very core of scientific inquiry itself. Just consider this. What language does the universe speak? As it turns out, that fundamental language is mathematics. Physicist Eugene Wigner famously described this phenomenon in his seminal paper, calling it the unreasonable effectiveness of mathematics in the natural sciences. Why do abstract concepts, born entirely within the human mind, things like numbers, vectors, and differential equations, describe the real world with such astonishing accuracy? The movement of planets obeys the elegant laws of Kepler and Newton. Electromagnetic waves are dictated by Maxwell's equations. The behavior of subatomic particles is governed by the Schrödinger equation. It seems the deeper we probe the mysteries of the cosmos, the more fundamentally mathematical the cosmos becomes. Some scientists, like cosmologist Max Tegmark, take this idea a step further, proposing the mathematical universe hypothesis. Tegmark suggests that our physical reality is inherently a mathematical structure. It's not just described by mathematics, it is mathematics. From the perspective of the simulation hypothesis, this observation takes on a profound new meaning. If the universe is a computer program, then it is entirely natural that its core operational language is mathematical. Any program is essentially a complex set of algorithms and mathematical operations, processing information represented by numbers. Our physical laws could simply be the high-level manifestations of this underlying mathematical code. When physicists discover a new formula describing some phenomenon, they might simply be reverse engineering fragments of our reality's source code. This also explains why the universe appears so logical, consistent, and knowable. It was designed that way. It operates by distinct rules because it is a simulation, not a chaotic and irrational world. This idea lends new weight to the famous words of Galileo Galilei, who stated that the book of nature is written in the language of mathematics. Perhaps he was right in a more literal sense than he ever could have imagined. We, as scientists, are simply learning to read this great book, attempting to understand the design of its author, or, as we might call them today, the programmer. For a moment, let's step back from the rigor of hard science and dive into those strange, unexplained phenomena in our everyday lives, the ones commonly labeled as glitches in the matrix. Naturally, we should approach these concepts with a healthy dose of skepticism. After all, the vast majority can be explained by the peculiar workings of our own psychology, memory, and perception. Nevertheless, within the context of a lecture on simulation theory, it's fascinating to explore them purely as a thought experiment. Take, for example, the phenomenon of déjà vu, that sudden, fleeting feeling that you have been in this exact situation before, even though, rationally, you know it's impossible. Psychologists offer various explanations, ranging from minor micro-seizures in the temporal lobe to simple misfires between short-term and long-term memory. But in the simulated world, déjà vu could be interpreted as a genuine system error, a moment where the system accidentally loads an old save file or cached data, creating that false sense of repetition. Or perhaps the simulation was rebooted from a specific point, and your consciousness retained a residual trace from the previous run. Another popular phenomenon is the so-called Mandela effect. This is a collective false memory, where a large group of people distinctly recalls an event that never happened, or recalls it differently from how it actually occurred. The name, of course, comes from the widespread false memory that Nelson Mandela died in prison sometime in the 1980s. Under the simulation hypothesis, the Mandela effect could be interpreted as the result of the developers making changes to the past's code, retroactively altering certain facts. However, much like a software update, not all traces of the old version were entirely wiped from the system's memory, which in this case is human consciousness. Naturally, there are more mundane explanations, usually related to confabulation and the viral spread of misinformation. We also hear anecdotal accounts of unexplainable coincidences that seem too improbable to be chance, or minor physical glitches where an object momentarily vanishes and then reappears. It's crucial to understand that none of this constitutes proof. These are strictly anecdotal accounts, easily dismissed as tricks of the mind. But if we accept the premise that we live in a simulation, then no program, no matter how perfect, is immune to bugs, errors, and crashes. And perhaps these fleeting, strange moments are those rare instances when we are actually able to glimpse behind the curtain of our meticulously rendered illusion. Let's assume the simulation hypothesis is valid, just for a moment. If we accept this premise, the obvious next question immediately arises: who are they? Who are these programmers, architects, or creators of our reality? Any discussion on this topic is, of course, pure speculation, but it's a fascinating exercise in imagination. The first and perhaps most compelling theory suggests they are our own descendants. This is known as the ancestor simulation scenario. Imagine a distant future where humanity has achieved a post-human phase, possessing unimaginable computational power. Perhaps they wish to study their past, to understand how their ancestors lived and which key decisions ultimately led them to become who they are now. The best way to do this? Run a detailed historical simulation. In this scenario, we are merely historical characters within their vast research project. The second possibility involves an extraterrestrial civilization. Perhaps a highly advanced race exists somewhere in the base reality who decided, for their own reasons, to construct our universe. Maybe for them, it's a scientific endeavor to study the emergence of life and consciousness under specific physical parameters. They might have spun up countless universes with varied starting conditions and physical laws, simply to observe the outcome. Our universe is just one of many running inside their cosmic laboratory. The third possibility is even more exotic. The creators might not be biological entities at all, but rather a super-intelligent artificial intelligence. In the base reality, some earlier civilization may have created an AI, which then surpassed its creators and began running simulations for its own inscrutable goals. Alternatively, the creators could be beings from another universe entirely, governed by completely different physical laws. Our world might be nothing more than entertainment for them, a complex video game, or a work of digital art. It's also crucial to remember that our creators don't necessarily have to be omnipotent and omniscient, like the gods found in traditional religions. They could simply be ordinary scientists, students, or even teenagers from a much more advanced world. Maybe our simulation is just someone's PhD thesis or a high school assignment. This thought is simultaneously humbling and, in a strange way, liberating. It strips our existence of the burden of cosmic significance and allows us to view life with a certain degree of irony, like a game. Continuing our contemplation of the nature of our hypothetical creators, we arrive at an equally crucial question: why? What is the purpose behind creating such an intricate and massive simulation like our own universe? The motives could be incredibly diverse, and we can only really speculate based on our limited human analogies. One of the most popular theories, as we've mentioned, is scientific research. The simulation might simply be a tool used to explore various fields of knowledge. If it's an ancestor simulation, the goal is history. If launched by an advanced alien civilization, it could cover cosmology, sociology, or biology. They might have set the initial conditions of the Big Bang and are now simply observing how cosmic evolution unfolds, how galaxies, stars, planets, and ultimately life are formed. In this light, we are essentially lab rats in a massive scientific experiment. Another possible reason is pure entertainment. We ourselves are constantly creating increasingly realistic video games and virtual worlds for recreation. For a civilization possessing virtually limitless computational resources, creating an entire universe populated by billions of conscious yet non-player characters, or NPCs, might be the ultimate form of leisure. In this scenario, our lives, our dramas, our wars, our love, and our suffering are merely compelling plot points for an external audience. That thought naturally is not very comforting. The third version involves modeling the future or solving complex problems. Perhaps the creator's civilization is facing some sort of global threat or grappling with a critical choice. They could be running simulations to test various scenarios and find the optimal solution. Our reality might simply be one of those crucial test runs. The fourth, and perhaps more philosophical reason, is art or self-discovery. Perhaps our universe is a grand work of art, created not for any utilitarian purpose, but simply for the sake of its inherent beauty and complexity. Or perhaps the creators, having reached the limits of their own development, launched simulations to explore the very nature of consciousness, creativity, and meaning. Finally, we cannot rule out the truly strange possibilities. Maybe our universe is a prison, or a form of purgatory, or a rehabilitation program for certain entities. Or, as some speculate, we might be part of a simulation that is itself a component of a much larger calculation, solving some problem for our creators without even realizing it. Ultimately, the true motives of the creators may be entirely incomprehensible to us, just as our own human motives are incomprehensible to an ant or to a character inside a computer game. When the concept of simulation comes up, the first thing most of us picture is the movie The Matrix. Physical bodies lying in pods, their brains plugged into a virtual world. This is known as a full immersion simulation, designed to simulate conscious experience rather than the physical world itself. However, this is only one potential scenario. Let's explore the different types of simulation hypotheses. The first type is the Matrix-style simulation. In this scenario, a base reality exists, housing our creators and the supercomputer running the program. Our consciousnesses, meanwhile, exist as information being processed by that machine. Our bodies and the entire surrounding world are just part of the illusion. This type is computationally cheap because it doesn't need to simulate every single atom in the universe. It only needs to simulate what the conscious subjects actually perceive. The second type is the microscopic simulation. Here, the simulation operates at the most fundamental level, down to quantum fields or the very pixels of space-time. The entire cosmos, with all its galaxies, stars, planets, and life forms, is contained within one enormous computer program. Crucially, we are not merely plugged into this simulation, we are fundamentally made of it. Our bodies and brains consist of simulated particles obeying simulated laws of physics. Our consciousness is an emergent property of this highly complex, simulated system. This model demands unimaginable, practically infinite computational resources, which is precisely why critics of the hypothesis find it the most implausible. Next, we have the third type, the hybrid or partial simulation. Perhaps the simulation doesn't encompass the entire universe. For instance, as we discussed in the context of the Fermi Paradox, the simulation might be confined to just our solar system, with everything beyond that being little more than background scenery. Alternatively, the simulation might only be highly detailed at the micro level, where observers, that is, living beings, are present, utilizing cruder, computationally cheaper modeling for the rest of space. The fourth type is the single brain, or solipsistic simulation. In this extreme case, only your consciousness is being simulated. The entire world, including me, speaking these words and everyone you know, is merely a construct created specifically for your experience. This scenario is impossible to prove or disprove, and it serves as the modern counterpart to the philosophical concept of solipsism itself. The choice between these simulation types carries significant consequences. In a matrix-style simulation, for example, we potentially have a real body existing somewhere in the base reality. In contrast, in a microscopic simulation, we are entirely and fundamentally products of the program. The simulation hypothesis gained widespread notoriety outside of purely academic circles, largely thanks to one person, Elon Musk. The founder of SpaceX and Tesla has repeatedly stated in interviews and public appearances that, in his view, the probability of us living in a computer simulation is close to 100%. Let's break down his core argument, which is essentially a popularization and simplification of the ideas put forward by philosopher Nick Bostrom. Musk's primary claim centers on what he calls the rate of development argument. He asks us to consider the evolution of video games over the past few decades. 40 years ago, we had Pong, just two rectangular paddles and a dot on a screen. Today, we have photorealistic 3D games supporting millions of simultaneous players and virtual reality that is becoming increasingly indistinguishable from actual reality. If we assume this pace of technological progress continues, even if it slows down by a factor of 1,000, then in just 10,000 years, a negligible amount of time on an evolutionary scale, we will be able to create simulations that are absolutely indistinguishable from reality. Musk then applies probabilistic logic. If it becomes possible to create such simulations in the future, then countless numbers of them, billions, will be created, and each one will be capable of housing simulated consciousnesses. Consequently, the number of simulated realities will far outweigh the number of base realities. From this, he concludes that the odds of us being in the one, original, true base reality are vanishingly small, perhaps 1 in billions. For Musk, this isn't just an abstract philosophical exercise. He actually believes we should hope we are living in a simulation. Why? Because if we are not in a simulation, he argues, it implies that civilization ceased to exist for some reason and never reached the stage where it could create such simulations. In other words, if reality is truly authentic, some sort of catastrophe likely awaits us. Thus, the simulation hypothesis is, paradoxically, an optimistic outlook on the future for him. Of course, Musk's argument is open to criticism. He makes a rather bold assumption about both the continuation of technological growth rates and the willingness of future civilizations to create these specific types of simulations. Nevertheless, his authority and popularity have played a crucial role in pushing this seemingly fantastical idea into the realm of serious public discussion. Despite its undeniable intriguing appeal, the simulation hypothesis faces heavy scrutiny from many scientists and philosophers. One of the most powerful counterarguments hinges on the philosophical principle known as Occam's razor. This principle, articulated back in the 14th century by the English philosopher William of Ockham, states, entities must not be multiplied unnecessarily. Simply put, when two theories equally explain the same phenomenon, you should choose the simpler one, the one that requires fewer assumptions. Let's apply Occam's razor to the problem at hand. We have the universe that we observe. The standard scientific model explains it through the Big Bang, evolution, and the laws of physics. This is a self-contained explanation. The simulation hypothesis offers an alternative. Our universe is a program running on a supercomputer in another base reality. But notice how many new, unprovable entities we are forced to introduce. First, we must assume the existence of this base reality itself, a reality we know nothing about and can never observe. Second, we must assume the existence of a creator civilization within that reality. And third, we need the supercomputer itself, capable of simulating our entire universe. The simulation hypothesis fails to explain the origin of reality. It merely shifts the problem up one level. Where did the base reality come from? How did it originate? What laws govern it? We aren't answering the fundamental question. We are just replacing it with an even more complex and convoluted one. Critics argue that this makes the concept less of a scientific hypothesis and more of a metaphysical or even theological one. It is unfalsifiable, meaning it cannot be disproven. Any argument against the simulation can be countered simply by saying, that's just how it was programmed. If we find no glitches, it means the program is written very well. If the laws of physics seem natural, it's because the simulators took great care to make them so. This stance, according to critics, pushes the hypothesis outside the bounds of science, turning it into a kind of modern myth or article of faith. Therefore, from the perspective of Occam's razor, the simulation hypothesis is an unnecessarily complicated and cumbersome construct compared to the standard scientific view of the world. The sheer challenge of computational power deals another serious blow to the simulation hypothesis, particularly the version that requires microscopic modeling of the entire universe. Let's try to estimate, even crudely, the kind of computational hardware we'd need for this task. Physicists estimate there are roughly 10 to the power of 80 elementary particles in the observable universe. To simulate the behavior of every single one of them, you'd need to store information about its state, position, momentum, spin, and so on. Furthermore, you'd have to constantly calculate the interactions between all these particles. The sheer scale of the necessary computations is simply beyond human comprehension. MIT physicist Seth Lloyd calculated that simulating the entire history of our universe, starting from the Big Bang, would require a computer that is physically larger than the universe itself. Crucially, it would also need to perform calculations faster than the speed of light. This results in a logical paradox. To simulate the universe, you need hardware that cannot physically exist within the constraints of the system you are simulating. Naturally, simulation proponents might counter that the laws of physics in the base reality, where the actual computer resides, could be entirely different. Perhaps they possess methods of computation that are currently unthinkable to us. However, this immediately invokes the problem of Occam's razor. We are introducing untestable, speculative assumptions solely to preserve the theory. Beyond classical limits, there's the critical issue of quantum computation. As established, quantum systems can exist in a superposition of multiple states simultaneously. Simulating these systems using a classical computer requires an exponential increase in resources. To accurately simulate just a few hundred interacting quantum particles, you would need a computer containing more atoms than are currently found in the entire observable universe. This means that accurately simulating our world demands a quantum computer of truly astronomical, impossible proportions. Physicists like Sabine Hossenfelder view this as perhaps the most compelling argument against the hypothesis. She argues that while we can certainly create simple simulations, the notion that one could simulate reality at the same level of complexity as reality itself is mathematically and physically untenable. It's akin to trying to construct a precise one-to-one scale model of an aircraft while confined entirely within that same aircraft. Let's return to Nick Bostrom's probabilistic argument and examine one of its most fascinating and mind-bending corollaries, the argument for nested simulations, or recursive simulations. This argument, paradoxically, can be used both to support and to undermine the simulation hypothesis. The logic flows as follows: if we accept that our civilization lives within a simulation, and if we ourselves can eventually create simulations that are virtually indistinguishable from genuine reality, then the simulated beings within our reality could also create their own simulations, and so on indefinitely. This results in an infinite regress, or a hierarchy of simulations nested within each other, like Russian stacking dolls. This scenario raises several serious issues. First, with every new level of nesting, the computational power available for the simulation must be carefully distributed. The processor of the host reality must simultaneously support our simulation, the simulations within ours, and all subsequent layers. This implies that the deeper we are within this stack, the lower the fidelity and detail of our reality must necessarily become. Some physicists, notably Zohar Ringel and Dmitry Kovrizhin, published research mathematically demonstrating that simulating certain quantum phenomena requires computational resources that grow exponentially with the number of simulated particles. They concluded that creating a complex simulation, such as the one we seem to inhabit, using a classical computer, is fundamentally impossible in principle. This finding deals a significant blow to the idea of infinite regress. Secondly, there is the crucial question of where this regress ends. Must there be some inherent limit to the depth of nesting? Perhaps at a certain level, the simulations become so simplified and unstable that intelligent life capable of creating new simulations cannot arise. Or perhaps there is some imposed law or rule instituted by the host reality that prevents simulated realities from creating their own simulations, specifically to avoid this paradox. On the flip side, the very fact that we appear to be approaching the ability to create our own convincing high-fidelity simulations can be seen as an argument that we are not too deep within this stack. If we were at the 100th level of nesting, perhaps the laws of physics in our world would be so fundamentally simplified that the development of complex technology would be impossible. Thus, the nested simulations argument transforms the hypothesis into an even more complex and intricate structure, rife with paradoxes and unresolved questions. If we are living in a simulation, the most compelling question is, can we prove it? Can we hack the matrix, find its source code, or at least detect subtle signs of its artificiality? Some scientists believe it is possible and have proposed specific experiments. The core idea is to search for the seams, or artifacts, that would inevitably arise due to the computational limits of the system running our reality. One of the most well-known tests was put forward by physicist Silas Bean and his colleagues at the University of Washington. Their theory rests on the assumption that if space is discrete, if it's essentially a 3D grid or lattice, this should be evident in the behavior of ultra-high energy particles. Specifically, they hypothesized that this grid would violate the symmetry of space. In continuous space, the laws of physics are the same in all directions. But a discrete grid might have preferred directions, aligned with the grid's axes. The researchers theorized that cosmic rays, those extremely high-energy particles arriving from deep space, would interact differently with this grid depending on their direction of travel. This interaction should result in anisotropy, meaning an uneven distribution of these rays across the celestial sphere. They even calculated a specific energy threshold above which this effect should become noticeable. However, subsequent observations of the highest energy cosmic rays revealed no such anisotropy. They appear to reach us uniformly from all directions. This finding is considered a powerful argument against a simple simulation model based on a cubic lattice. Another approach involves trying to detect changes in fundamental physical constants. If our universe is a simulation running on someone else's computer, perhaps the system administrator occasionally pushes patches or code updates. These updates could cause small, measurable fluctuations in values like the fine structure constant or the gravitational constant. Scientists have been conducting extremely precise measurements of these constants for years, but so far, no compelling evidence of variation has been found. Of course, all these tests rely on our current understanding of how such a simulation would operate. Maybe our creators are far more sophisticated, employing technology that leaves no obvious seams. Or perhaps they simply don't want us to know the truth and are actively hiding the evidence. Let's continue exploring the experimental avenues for testing the simulation hypothesis. Beyond looking for anisotropy in cosmic rays, there are other, more subtle approaches. For instance, some theoretical physicists working in quantum gravity suggest that the fundamental discreteness of spacetime at the Planck scale could lead to fascinating optical effects. The idea is that light of different wavelengths, that is, different colors, might travel through this pixelated structure at slightly varying speeds. This effect would be entirely negligible over earthly distances, but for light traveling to us from extremely distant objects, such as gamma-ray bursts that occurred billions of light-years away, this tiny difference in speed could accumulate and become noticeable. We might observe high-energy gamma rays arriving slightly sooner or slightly later than low-energy visible light photons, even though they were all emitted at the exact same moment. Several astronomical observatories like the Fermi Gamma Ray Space Telescope are actively looking for such anomalies in light dispersion. To date, the results have been inconclusive, and no convincing evidence of a violation of the constant speed of light principle has been found. Another fascinating idea involves searching for the universe's source code. Working on superstring theory, theoretical physicist James Gates Jr. discovered structures in the equations describing fundamental particles that are strikingly similar to error correction codes, special algorithms used in computer systems to detect and fix data transmission errors. Gates wondered why would error-correcting codes be necessary in the mathematical description of physical reality? He jokingly suggested that maybe we really are living in a simulation, and these codes are part of its underlying framework. Of course, for now, this remains a compelling analogy rather than hard proof. There are also proposals to actively search for glitches or deliberate Easter eggs left behind by the supposed developers. For example, by creating extreme conditions in particle accelerators, we might attempt to break the simulation or force it to reveal its hidden parameters, but all of this remains strictly within the realm of bold hypotheses. The main problem with all these experimental tests is that they only check for very specific and perhaps naive models of simulation. An advanced civilization could easily create a simulation based on continuous mathematics or on principles that we cannot even begin to imagine. In that scenario, all our attempts to find pixels or glitches would be doomed to fail. Let's suppose for a moment that tomorrow scientists unequivocally prove that we are living inside a simulation. How would this discovery impact our lives, our society, and our fundamental understanding of ourselves? The philosophical and ethical ramifications of such knowledge would be monumental. First and foremost, it would shatter our sense of reality and significance. If our world isn't real and our joys and sufferings are merely part of someone's experiment or entertainment, does our life hold any meaning at all? Many might plunge into a state of nihilism and despair, concluding that since nothing is real, no actions truly matter. Why strive, build, or love if at any moment the administrator could simply hit the off button? On the other hand, for some, this knowledge could be liberating. If life is just a game, perhaps we should take it less seriously and not view failures so tragically. It might encourage greater creativity, experimentation, and a search for cheats and Easter eggs hidden within the game's code. Another critical question revolves around free will. If we are characters within a program, how much genuine freedom do we have in our decisions? Are our actions predetermined by the simulation's initial code and parameters, or do we possess some degree of autonomy? The answer to this would fundamentally alter our concepts of responsibility, justice, and morality. If a criminal committed an atrocity because they were programmed to do so, can we truly hold them accountable? Ethical questions also arise concerning our creators. If they exist, do they bear moral responsibility for all the suffering that takes place in our world? If they engineered a world complete with disease, war, and death, aren't they, in a sense, monsters? Or are they merely dispassionate observers for whom our suffering is no more significant than the agony of characters in a violent video game? This knowledge could also lead to the rise of new religions and cults. People might begin worshipping the programmers, attempting to contact them, praying for mercy, or even begging for patches to fix the imperfections of our world. Society might fracture into those who long to wake up and escape the matrix, and those who prefer to remain in blissful ignorance within a comfortable illusion. Ultimately, the realization of our simulated nature would likely be the greatest upheaval in human history, forcing us to completely reassess everything we once believed to be true. The concept that our world was created by someone and operates according to set laws is far from new. It underpins most of the world's major religions. In this context, it is fascinating to draw parallels between the simulation hypothesis and traditional theological concepts. Initially, the analogies seem obvious. In the simulation hypothesis, the role of the omnipotent, omniscient, and omnipresent God is filled by the programmer or architect of the matrix. This entity created the world from nothing, or more accurately, from code, established its laws, which are the physical constants, and observes its unfolding development. Certain religious texts describing the creation can even be read as a metaphorical description of launching a computer program. However, a deeper examination reveals crucial differences. First, the deities of most religions are typically described as transcendent, immaterial entities existing outside of space and time. The creators of the simulation, however, are likely physical beings living in their own base reality, bound by their own set of physical laws. They could be mortal, limited in their knowledge and abilities. They are not necessarily omnipotent, their capacity is limited by the computing power available to them. Second, religious concepts often incorporate the idea of divine providence, moral law, and post-mortem reckoning. God didn't just create the world, he actively intervenes in its affairs, guides history, rewards the righteous, and punishes the wicked. In the simulation hypothesis, such interference is not guaranteed. The creators might be passive observers who simply launched the program and then stepped away. They may not care about our morality, and concepts of good and evil, as we understand them, might not exist for them. Third, the simulation hypothesis offers a fundamentally different explanation for miracles and supernatural events. In religion, these are manifestations of divine power that override the laws of nature. In a simulation, they could be glitches, cheat codes, or deliberate interventions by an administrator simply editing the reality code. Despite these differences, the simulation hypothesis can be viewed as a modern, secular, and technological version of deism, a philosophical doctrine that acknowledges a creator God but rejects his interference in worldly affairs. This is the watchmaker God who crafted the mechanism of the universe, wound it up, and left it to run on its own. In our context, this is the programmer God who wrote the code and launched the simulation. The so-called problem of evil stands as one of the most persistent and challenging questions in philosophy and theology. If an omnipotent, omniscient, and benevolent God truly exists, then why do we see so much evil and suffering in the world, the sickness, the wars, the famine, the natural catastrophes? Various religions and philosophical schools offer their own answers, often pointing to human free will, a divine plan beyond our comprehension, or the existence of an evil force opposing the divine. The simulation hypothesis, however, offers a completely different and, frankly, quite disturbing perspective on this conundrum. If our world is merely a simulation, the suffering within it might be explained in several unsettling ways. The first, simplest, and most cynical possibility is that our creators simply don't care. If we are nothing more than characters in a massive game or data points in an experiment, our pain holds no moral weight for them. An academic studying an ant colony feels no moral turmoil when one ant kills another. It is simply an observed fact. In the same way, our programmers might be watching our wars and pandemics with cold, scientific interest, merely logging the data. The second explanation is that suffering might be a necessary component of the simulation itself. If the goal is to accurately model ancestral history or study evolution, the simulation must include all the negative aspects of life. A simulation of paradise, where everyone is happy and nothing ever happens, would be useless from a research standpoint. Conflicts, the struggle for survival, disease, these could all be integral parts of the experiment. A third, even bleaker theory suggests that suffering is the end goal itself. Perhaps our simulation was created by sadistic beings who find our torments entertaining. We might be gladiators in their cosmic colosseum. Or alternatively, this simulation could be a form of punishment, a kind of hell or purgatory for some other, perhaps guilty, consciousnesses. Of course, a more optimistic option also exists. Perhaps our creators are highly moral beings who suffer alongside us as they watch our troubles unfold, but they refuse to intervene because doing so would contaminate the experiment or violate our essential free will. Regardless of the specific mechanism, the simulation hypothesis fundamentally removes the necessity of a benevolent creator. The architect of our world is not required to be good. They could be a scientist, a gamer, an artist, or even a madman. And this realization forces us to confront a vital truth. If we want to make our world better and reduce suffering, we can ultimately only rely on ourselves. At the heart of our existence lies consciousness, that subjective sense of self, our thoughts, feelings, and experiences. The mystery of consciousness remains one of the deepest enigmas in science and philosophy. How does an inner world arise merely from a collection of electrical and chemical signals within the brain? The simulation hypothesis offers a radically new approach to this problem. Specifically, what is consciousness within the context of a simulation? There are two primary scenarios. The first posits that consciousness itself is not simulated but rather exists external to the simulation. This is the classic matrix or brain in a vat model. In this case, we are real conscious entities residing in the base reality, and the simulation is merely a stream of information fed into our brains, or their equivalent, creating the illusion of this world. This scenario suggests that consciousness has a fundamental nature, something irreducible to mere computation. The second scenario, which seems more probable in the context of a microscopic simulation, proposes that consciousness is itself a product of the simulation. That is, it is an emergent property of an extremely complex computational system. Just as a complex character AI in a video game emerges from the interaction of countless simple algorithms, our consciousness may be the result of a simulated brain, composed of simulated neurons, which are, in turn, composed of simulated atoms. In this model, we have no real body or brain outside the simulation. We are entirely and exclusively information, a pattern running on a gigantic computer. This idea is closely linked to the so-called computational theory of mind, which asserts that consciousness is fundamentally a process of information processing. If this theory holds true, there is no fundamental difference between consciousness arising on biological hardware, like our brain, and consciousness arising on silicon hardware, like a computer. Any sufficiently complex system processing information in the requisite way could be considered conscious. This viewpoint has astonishing implications. It means consciousness could be copied, transferred to a different medium, paused, and restarted. Your self is not your body. It is the unique informational pattern that defines you. In a simulated universe, death might not be an end, but merely the termination of a specific process, a process that could potentially be run again. Let's delve into one of the most radical and disturbing interpretations of the simulation hypothesis, one that is deeply intertwined with the classic philosophical problem of solipsism. Solipsism is the idea that only my own consciousness exists, and the entire external world, including all other people, is merely a figment of my imagination or a dream. This position is logically impossible to disprove. Any argument presented to you by another person must be processed through your own consciousness, and thus could simply be part of your illusion. The simulation hypothesis offers a technological version of this idea. Imagine a so-called solipsistic simulation or a single-player simulation. In this scenario, a supercomputer isn't simulating the entire universe with billions of conscious minds, but only your personal experience. The entire world you see, every person you interact with, including the voice you're currently hearing, are nothing more than sophisticated non-player characters, or NPCs, generated by the program purely for interaction. You are the sole player, the only true center of consciousness in this reality. Such a simulation would be far more computationally economical than simulating an entire universe. The system would only need to render the world from your perspective and simulate complex behavior only in the people you directly interact with. Everything else could exist as simplified background processes. This idea is terrifying because it reduces all your loved ones, your friends, and even all of human history and culture into mere set dressing. Your relationships, your love, your struggles, they are all interactions with highly advanced, yet soulless, chatbots. On the other hand, this makes you the center of the universe in the most literal sense. This entire grand simulation was created specifically for you, but to what end? Perhaps you are a subject in some kind of psychological experiment. Maybe you are an artificial intelligence being trained by immersion in a realistic environment. Or perhaps you are the creator of this simulation yourself, someone who decided to dive in and erase their own memory in order to gain a truly authentic life experience. Like classical solipsism, this hypothesis is impossible to verify. Any attempt to prove that other people possess consciousness would occur inside the simulation and could therefore be part of it. The only thing you can be certain of, according to Descartes, is the existence of your own thinking self, your cogito. Everything else remains in question. The rapid development of technology, particularly quantum computing, is lending far more weight and credibility to the simulation hypothesis. Classical computers, which our current civilization relies on, operate using bits, units of information that can exist in one of two distinct states, 0 or 1. Quantum computers, however, operate on entirely different principles. They utilize qubits, or quantum bits. Thanks to the principle of superposition, a qubit can exist simultaneously as a 0, a 1, and any combination in between. This allows quantum computers to perform certain types of calculations exponentially faster than classical machines. Why is this crucial to our discussion? First, as we've already established, one of the primary obstacles for the simulation hypothesis is the sheer computational power needed to model the quantum phenomena of our world. This is virtually impossible on a classical computer. But if we assume that the supercomputer running our universe is itself a quantum computer, that problem instantly disappears. A quantum computer can efficiently simulate a quantum reality. Our universe looks quantum perhaps because it is running on quantum hardware. Second, the development of our own quantum computers makes the very idea of creating advanced simulations far more realistic. If we manage to build a sufficiently powerful quantum computer, we could potentially simulate small pocket universes with their own unique laws of physics. And if we can do that, then according to Bostrom's logic, it increases the probability that someone before us has already done the same, meaning we are currently inside such a simulation. Some scientists take this idea even further. Physicist Vlatko Vedral, for instance, suggests that the universe isn't just simulated on a quantum computer. The universe is the quantum computer. In this worldview, elementary particles are the qubits, and their interactions, governed by the laws of physics, are the quantum computations. The entire history of the universe, from the Big Bang to the present day, is one giant quantum calculation. What exactly is it calculating? That's the ultimate question. Perhaps it's computing itself, predicting its own future. In this concept, reality and simulation become fundamentally indistinguishable. Our world is simultaneously a physical reality and an information processing system. When discussing the simulation hypothesis, it is useful to examine closely related alternative ideas that similarly challenge our conventional view of reality. One of the most intriguing of these is the holographic principle. This concept emerged from studies of black holes and string theory. In short, its essence is this: all the information contained within a three-dimensional volume of space can be entirely described by its two-dimensional boundary. Think of a standard hologram. It is a two-dimensional plate, but when illuminated by a laser, it generates a full three-dimensional image. The holographic principle suggests that our universe might be structured in a similar way. Everything we perceive as a three-dimensional world, galaxies, stars, planets, and even ourselves, might be nothing more than a holographic projection of information encoded on some distant two-dimensional surface surrounding our universe. How does this connect to the simulation hypothesis? On one level, these are distinct concepts. The simulation hypothesis posits that our reality is the result of computation. The holographic principle suggests that the information defining our three-dimensional reality can be encoded in fewer dimensions. On the other hand, these ideas can be mutually supportive. If our universe is a hologram, simulating it becomes significantly easier. The programmers wouldn't need to simulate the entire three-dimensional volume of our world. They would only need to simulate the information on that two-dimensional boundary surface. This drastically reduces the required computational resources and memory storage. In a way, the universe itself employs a form of data compression. This idea resonates with how computer technology already operates. For instance, in 3D graphics, complex three-dimensional objects are often rendered using two-dimensional textures applied to simpler geometry. The holographic principle is essentially the application of this same concept on a cosmic scale. Thus, while the holographic principle doesn't prove that we live in a simulation, if true, it makes the idea far more plausible from a technical feasibility standpoint. It offers yet another strong hint that information might be fundamental to our reality, and that the three-dimensional space we inhabit might not be as fundamental as we assume. Our world could perhaps be both a simulation and a hologram. The question of what happens after we die has captivated and troubled humanity for millennia. Traditional religions paint varied pictures: heaven, hell, reincarnation, or merging with the absolute. The strictly atheistic viewpoint assumes consciousness simply ceases to exist entirely. The simulation hypothesis, however, throws several new and intriguing possibilities into this mix. If we are indeed living inside a massive computer program, what happens when a simulated character dies? To explore this, let's consider several scenarios using analogies from standard computer systems. The first option is complete deletion. When a character dies in a video game, their data is often simply erased from the system's memory to free up resources. In this case, death within the simulation is equivalent to absolute and final non-existence. Our informational pattern, our very consciousness, simply ceases to be. This is the most straightforward and arguably the most likely scenario. The second option is save and restart. Perhaps the data associated with our consciousness isn't deleted, but rather archived and stored somewhere on the supercomputer's hard drive. If this is the case, the creators have the ability to resurrect us, meaning they could restart our simulation from the moment of death or load us from any previous save point. This might be done for further analysis, or perhaps we could be seamlessly transferred into an entirely new simulation. This scenario opens the door to a form of digital immortality. The third option is reincarnation. Our core consciousness, or its fundamental structural pattern, might be recycled and reused to create a new player character. This is similar to games where, upon death, you start over, perhaps retaining some archived skill sets, but without any memory of the previous life. If this model holds true, we would be destined for an endless cycle of rebirth within the simulation itself. The fourth option is the exit strategy, or logging off. Perhaps death is the very mechanism designed to allow us to exit the simulation and wake up in the base reality. Our life here might be seen as a specialized training program, a specific test, or a grand game. Upon completion, we simply return to our true native world. This is easily the most optimistic version, transforming our entire existence into a temporary adventure with the ultimate goal of going home. Naturally, all of this is pure speculation. However, these ideas demonstrate how the simulation hypothesis fundamentally reshapes our most basic understanding of life and death, offering fascinating technological parallels to the ancient religious and esoteric concepts of the afterlife. If we are characters living within someone else's simulation, is there any way for us to connect with our creators? Can we send them a message, pose a question, or at least signal that we've realized the true nature of our reality? This concept, often called the developer communication problem, is one of the most fascinating aspects of the simulation hypothesis. On one hand, such communication might be fundamentally impossible. If we are entirely and exclusively products of the program, we may possess no tools whatsoever for interacting with the world outside of it. It's like a character in a game on your smartphone trying to send you an email. They operate only within the rules and boundaries hardwired into their code. Any attempt they make to break through the screen is simply an emergent part of their own programmed logic. On the other hand, perhaps the creators themselves have left behind some kind of communication channels or Easter eggs. Some theorize that certain mathematical or physical constants might contain an embedded encoded message. For example, a hidden message from the programmer might be encrypted within the digits of pi after the decimal point. The famous astronomer Carl Sagan explored this very idea in his novel Contact. However, to date, no such anomalies have been found within the fundamental constants. Another possibility involves intentionally attempting to overload the system. If we can create conditions in particle accelerators or through astrophysical phenomena that demand extreme computational power from the simulation, it might trigger a glitch or draw the attention of the system administrator. This is a risky strategy, as it could potentially lead to the entire system freezing or initiating a hard reboot. Some also suggest that mystical insights, religious revelations, or altered states of consciousness might constitute a form of contact with a higher level of reality. Perhaps during these moments, our simulated brains briefly gain access to outside information, but that, of course, remains outside the boundaries of the scientific method. There is also the opposing question: do the developers even want us to contact them? If we are part of a scientific experiment, our awareness of that fact could contaminate the data. In that case, the creators might actively impede any of our attempts to establish contact, perhaps even editing reality itself to hide the truth from us. Ultimately, we are much like the inhabitants of an isolated island who see airplanes flying high overhead, but have no mechanism whatsoever for understanding what they are or how to reach them. One of the biggest mysteries in modern cosmology is the so-called fine-tuning problem of the universe. The essence of the problem is that the fundamental physical constants governing the structure and evolution of our world have values that appear to be calibrated with incredible precision for the emergence of complex structures like stars, planets, and ultimately, life. For example, if the force of gravity were even a fraction of a percent stronger, stars would burn out much faster, leaving no time for life to evolve on their planets. If it were slightly weaker, stars and galaxies simply couldn't form at all. If the strong nuclear force was slightly different, the universe would contain nothing but hydrogen. If the ratio of proton mass to neutron mass were altered, stable atoms wouldn't exist. The list of such lucky coincidences is extremely long. It seems the universe is balanced precariously on a razor's edge, and the slightest deviation in its fundamental parameters would render it utterly sterile and lifeless. How do we explain this astonishing fine-tuning? There are several main approaches. The religious approach posits a divine design. God deliberately created the universe with laws optimized for the emergence of life. The scientific approach, known as the anthropic principle, suggests the existence of the multiverse, an enormous collection of universes, each governed by different physical laws. We naturally find ourselves in one of the rare universes where conditions are suitable simply because observers could not arise in the others. The simulation hypothesis offers a third, very simple and elegant explanation. If our universe is a simulation, then its parameters are not random. They were purposefully set by the programmers. And this is analogous to a game developer setting parameters in an engine, the strength of gravity, friction, or character speeds, to make the game engaging and playable. The creators of our simulation may have wanted to engineer a world where life and consciousness could emerge. They could have cycled through different constant values in a series of test runs until they found the precise combination that yielded the desired result. In this scenario, the problem of fine-tuning simply vanishes. The universe is tuned for life because it was deliberately tuned that way. This is one of the strongest circumstantial arguments in favor of the simulation hypothesis, as it transforms an improbable coincidence into the result of intentional design. The most unsettling aspect of the simulation hypothesis is the idea that our entire reality, all our achievements, all of human history, could vanish in an instant at someone else's whim. What if the simulation is simply turned off? What might be the triggers for such an apocalyptic event? The first and most obvious reason is the conclusion of an experiment. If our simulation was initiated with a specific scientific goal, say, tracking the evolution of life up to a certain stage, once that goal is met, the program might simply be halted and the collected data archived for analysis. For us, this would mean a sudden, absolute, and unannounced cessation of existence. The second reason is resource depletion. Any simulation demands energy and massive computational power. Perhaps a cataclysm or crisis occurs in the baseline reality, forcing the creator's civilization to shut down all non-essential projects, including ours, to conserve resources for their own survival. Alternatively, our project might simply be deemed too expensive or inefficient, and they decide it's time to cut their losses. The third reason involves outdated hardware or software. We constantly upgrade our own computers and operating systems. It's possible the supercomputer running us simply becomes obsolete. If the creators decide to migrate their projects to a newer, more advanced platform, our current simulation might be incompatible with the new architecture. It would be easier to delete us than to spend the resources adapting the old code. The fourth reason is us. Perhaps our development follows a path deemed dangerous or undesirable by the creators. For instance, if we manage to create our own super-intelligent AI, it might be perceived as a threat to the simulation's stability or even to the baseline reality itself. In this scenario, the creators might initiate an emergency shutdown. Alternatively, we could simply become boring. If the simulation was designed for entertainment and our evolution plateaus or becomes too predictable, the players might lose interest and simply initiate a new game. This existential threat is fundamentally different from the threats we usually worry about: nuclear war, asteroid impacts, or climate change. This is not the physical destruction of life within our world, but the annihilation of our world itself, the very fabric of reality, and we would be utterly powerless to stop it. This brings us to the final and perhaps the most crucial question. Okay, let's assume we do live in a simulation. So what? How should this knowledge, or even just this strong suspicion, affect our day-to-day lives? Should we change our behavior, our goals, or our fundamental values? At first glance, it might seem like the answer is nothing at all. Regardless of whether reality is base or simulated, our subjective experiences, pain, joy, love, and fear, are completely real to us. A headache is equally unpleasant whether it's the result of interacting real neurons or simulated ones. The joy of connecting with loved ones remains equally valuable, even if those loved ones are complex software constructs. The rules of our world, be they physical or programmed, continue to apply, and we are forced to obey them. As a character in the series Westworld famously put it, "If you can't tell the difference, does it matter?" From this perspective, we should simply continue living as we always have, striving for happiness, knowledge, self-improvement, and building a better society within our simulation. However, philosopher Nick Bostrom, the primary proponent of the hypothesis, suggests a slightly different approach. Bostrom believes that taking this hypothesis seriously places a certain moral responsibility upon us. For example, we should strive to run ethical simulations ourselves in the future, as this increases the probability that our own simulation is being managed by benevolent creators. Furthermore, he jokingly suggests making our lives more interesting for any potential external observers, lest they lose interest and decide to switch the program off. This might mean encouraging creativity, scientific achievement, and even a healthy dose of chaos. Another key aspect is the search for meaning itself. If our lives lack innate, cosmic meaning, then we are entirely free to create it ourselves. The meaning can become the game itself, exploring the rules of our world, attempting to understand it at the deepest possible level, and appreciating its complexity and beauty. Perhaps the highest goal of our existence is to recognize the nature of our prison, and if not escape it, then at least study every last detail. Ultimately, the simulation hypothesis does not necessarily lead to nihilism. On the contrary, it can give our lives a new, almost playful dimension, filling it with curiosity and wonder. It reminds us not to take reality for granted, and that the most incredible secrets might be hidden just behind the familiar facade of everyday life. And so our deep dive into the simulation hypothesis is now winding down. We've tracked how this profound idea, first conceived in the halls of philosophy, has found powerful new relevance in the digital age. We explored Nick Bostrom's famous trilemma argument, which statistically leads us to the conclusion that we are likely not inhabiting base reality. We dove into the curious world of quantum mechanics and saw how the observer effect and the discretization of space-time resemble optimization and pixelization within computer systems. We talked about the laws of physics as software code, the Fermi Paradox, suggesting the developers are reluctant to clutter the simulation with unnecessary entities, and the universe's fine-tuning implying deliberate design. However, we also addressed the serious counter-arguments. Occam's razor urges us against needlessly complicating our view of the world, while the monumental problem of computational power questions the very technical possibility of running such a grand simulation, it is crucial to remember that as of today, the simulation hypothesis remains exactly that, a hypothesis. It's a fascinating thought experiment that pushes the boundaries of our imagination, but it is not a proven scientific theory. We have zero direct evidence that our world is artificial, but at the same time, we have zero evidence to prove the opposite. We live within this fascinating ambiguity, which constantly compels us to ask the most fundamental questions. Who are we? Where do we come from? And what is reality? Thank you for spending this time with me, reflecting on one of the deepest mysteries of existence. I hope this lecture gave you plenty of food for thought and helped you unwind. If you enjoyed this philosophical journey, please hit the like button, subscribe to the channel so you don't miss future lectures, and share this video with anyone else who might find it interesting. Now, I want to leave you with a question to continue our discussion in the comments below. Imagine you had the chance to ask one single question to the creators of our simulation. What would you ask? Good night and sweet dreams, even if those dreams are just a simulation within another simulation.